Hi, my name is Harlan. Welcome to the H. Machacon Mechanical Engineering channel on YouTube. A couple of months ago, my niece, who is currently reviewing to take the licensure exam for a chemist, requested me to solve a problem about Carnot Cycle. And so I did, and it also inspired me to prepare lectures on thermodynamics. So here's the problem about Carnot cycle that I solved for her. Consider a Carnot cycle that is operated using a diatomic gas having a value of C sub P is equal to 3.5 times R, initially at 25 degrees Celsius, 100 kilopascals, and 0.01 cubic meters. The system is then compressed isothermally until the volume is 0.002 cubic meters. It is then compressed further into 0.001 cubic meters. What is the mean effective pressure in kilopascals? Given that R, the gas constant, is equal to 8.314 joules per mole degree Kelvin. So looking at the diagram, we have the temperature entropy diagram here, and also the pressure volume diagram. We can see from the temperature entropy diagram from point 1 to 2, we have the constant temperature line, and from point 2 to point 3, we have the constant entropy line, and another constant temperature line from point 3 to point 4, and from point 4 to point 1, we have a constant entropy line. Back to point 1. And we can show it here, the curves involved in the process from 1 to 2, 2 to 3, 3 to 4, and 4 back to 1. We can show it in the pressure volume diagram. So what are the properties that are given? First, T sub 1 is equal to T sub 2 is equal to 25 degrees Celsius plus 273. So we have 298 degree Kelvin. When we tackle problems about gases, thermodynamics, we always use the absolute values of the temperatures. And P sub 1 is given at 100 kilopascals, and V sub 1 is 0.01 cubic meters. V sub 2 is equal to 0.002 cubic meters. V sub 3 is 0.001 cubic meters. Cp is 3.5 times R. R is equal to 8.314 joules per mole degree Kelvin. So we will tabulate the given properties at each point. So the text written in blue are the given properties. You will notice at point 1 here, pressure, volume, and temperature. Point 2, volume and temperature. Point 3, we have the volume. So we will solve first for the specific heat at constant pressure. We have 3.5 times the gas constant R, 3.5 times 8.314 joules per mole degree Kelvin. The result will be 29.099 joules per mole. And then we solve for the specific heat at constant volume using the definition of enthalpy. So enthalpy is equal to internal energy plus flow work. So we have the derivative of enthalpy is equal to the derivative of internal energy times the derivative of flow work. So in terms of absolute temperature and specific heat values, we have specific heat at constant pressure times the differential of the absolute temperature. That will be equal to the differential of enthalpy here. And this, on the other side of the equation, we have specific heat at constant volume times the differential of the absolute temperature will be equal to the differential of the internal energy. And the derivative of flow work is equal to the gas constant R times the derivative of the absolute temperature. So we simplify by canceling dt here on both sides of the equation. The result will be Cp is equal to Cb plus R. And when we substitute the values, Cp 29.099 is equal to C sub V plus 8.314 joules per mole degree Kelvin. And solving for C sub V will be equal to 20.785 joules per mole degree Kelvin. Solve for K. That will be the next step for us to do. So K is equal to the ratio of specific heats, constant pressure, and constant volume. So 29.099 divided by 20.785, and the result will be 1.4. So this will be the ratio, specific heat ratio K is equal to 1.4. So we can now move on. So let's go and discuss process, the first process, which is from point 1 to point 2. We can see here the constant temperature line from point 1 to point 2 in the temperature entropy diagram. And we also represent here in the pressure volume diagram. And constant temperature line is actually equal to P times V is equal constant. Okay, and then so P sub 2 is equal to T sub 1. Pressure sub 2, volume sub 2 is equal to P1 V1, where solving for P2, we have this equation here. And substituting values when we solve for P2, 100 kilopascals, and this one is, the numerator is 0.01 cubic meters, the denominator is 0.002 cubic meters, and the result we'll get P2 is equal to 500 kilopascals. So we enter the value into our table here, 500 kilopascals. So we now have pressure, volume, and temperatures for points 1 and point 2, and then we move on to point 3. We can also solve the work output resulting from the constant temperature process from point 1 to point 2 here. Okay, so it is constant temperature, so PV is equal to constant. And then we will express pressure in terms of volume and the constant here. So manipulate our integral here. Substitute it into your equation, C over V for pressure. So we can put the constant C outside of the integral sign, and we have this one is easy to integrate. So we have this one, the C value is equal to P times V. So, and this one inside the integral sign, the result will be ln v from 0.1 to 0.2. So this will be the equation, and substituting the values, we can now get the result of negative 1.609 kilopascals times cubic meters. But what is kilopascals times cubic meter? 1 kilopascal is equal to 1 kilonewton per square meter. And 1 joule is 1 Newton meter. So this one, 1 kilonewton per square meter times cubic meters will be 1 kilonewton per times meter, and the result will be 1.609 kilopascals per square meter, or 1.609 negative kilojoules. Let's tabulate the result here. From process 0.2 to 0.3, we have isentropic compression. From 0.2 to 0.3, we can see the constant entropy line from 0.2 to 0.3, and we represent it also in the pressure volume diagram as PV raised to the K is equal to constant. So from process from 0.2 to 0.3, S sub 2 is equal to S sub 3. We have the PV raised to the K constant from 0.2 to 0.3. We're solving for P sub 3. We have this value here, P2 times the quantity V2 over V3 raised to the power K. And substituting the values, we can now solve for the value of P sub 3, 1,319.5 kilopascals. The next step is to solve for T sub 3 using this value, P3 V3 raised to the K, P2 V2 raised to the K. And we will manipulate this. We will separate one here. We'll put V sub 3. We'll separate it from the V sub 3 raised to the power K. So the one remaining here, on the right side, will be V sub 3 raised to the power K minus 1. So you will notice that if you manipulate this, if you simplify this, the result will be this. Same is true with the right side of the equation. And we know that P3 V3 will be equal to T sub 3. So this one, this value here, and we have T sub 2 here. So we can solve the values for T sub 3, knowing T sub 2, V sub 3, and V sub 2. Here. So substituting the values of T sub 2, V sub 2, V sub 3, and the value of K 1.4. So the result for T sub 3 will be 393.2 degree Kelvin. Here, tabulate the values in our table. We have 1,319.5 kilopascals and 393.2 degree Kelvin. So again, the values written in blue are the given values, and the values properties written in yellow are the ones that we have solved. So the next step is to calculate the work done in the process from point 2 to point 3. So from point 2 to point 3 here shown, the shaded area. So it is isentropic. So v raised to the power k is constant. So we manipulate our integral here by substituting the value of k in terms of volume v and the constant c. So this p is equal to c over volume raised to the power k. We substitute this value of k, value of p in our integral, so that we can put c to the outside of the integral sign, and this one will be v to the negative k times dv from point 2 to point 3. That will be now simpler to solve. So here, you see, we have p2 v2 raised to the power k, and we have v raised to the power 1 minus k all over 1 minus k from point 2 to point 3. And manipulating it, simplifying further, we have the work from point 2 to point 3 will be p sub 3 v sub 3 minus p sub 2 v sub 2 all over 1 minus k. And substituting the values, the result will be negative 0.7988 kilopascals times cubic meters, which is actually the same as negative 0.7988 kilojoules. From point 3 to point 4, we have an isothermal process, and we can see in representing it in the temperature entropy diagram, we can see the constant temperature line from point 3 to point 4. We can also represent it in the pressure volume diagram. Here, the curve from point 3 to 4, which is a PV is equal to constant curve. Okay, so T sub 4, because it's isothermal, is equal to T sub 3. We know already that T sub 3 is 393.2 degree Kelvin. Okay, and P sub 4 V sub 4 is equal to P3 V3, 1,319.5 kilopascals times 0.001 cubic meters, where we can solve for the value of P sub 4 here divided by V sub 4. So P sub 4 is equal to 1,319.5 kilopascals times 0.001 cubic meters all over V sub 4. We do not know V sub 4 yet. So what we will do in order to solve for V sub 4, we will find the relationship of V sub 4 and V sub 1 in terms of V sub 1, because we already know what V sub 1 is. Okay, so from point 4 to point 1, we have here an isentropic line from point 4 to point 1 in the TS diagram. We can represent it in our pressure volume diagram. This curve here from point 4 to point 1, P V raised to the K is constant. So S sub 4 is equal to S sub 1. So P4 V4 raised to the power K is equal to P1 V1 raised to the power K. So we know that K is 1.4. So we can solve is 100 kilopascals times quantity of 0.01 cubic meters raised to the power 1.4. And P4 is equal to this value divided by V4. Hence, we know now the value of, we can now solve, because the only variable here is V sub 4, we can now solve this value V sub 4 in using this equation, and the value of V sub 4 is 0.005 cubic meters here. And since we know now V sub 4, we can also solve for P sub 4. Okay, so we substitute the values. 1319.5 kilopascals times 0.001 cubic meters all over 0.005 cubic meters, and the value of P sub 4 will be 263.9 kilopascals. So we tabulate the values in our table. So the properties are now complete for each point, 1, 2, 3, and 4. You have pressure, volume, and temperature. So the next one is to determine the work done from the process from point 3 to point 4 here. In the shaded portion will be the work done. So integral of PdV from point 3 to point 4. We know that this is an isothermal process, so P for PV is equal to constant, and we manipulate the integral here by replacing the value of P with constant over B. See, constant over B. We replace it in the value of P here for the integral. So we can put the constant outside the integral sign here, and dV over V, the integral which is ln of V from point 3 to point 4, and we have PV is equal to constant. So simplifying further, we have P3 V3 ln V4 over V3. Substituting the values, 1319.5 times 0.001 cubic meters times the ln of 0.005 cubic meters divided by 0.001 cubic meters, and the result will be this 2.124 kilopascals times cubic meters, which is actually the same as 2.124 kilojoules. Okay, so we will now tabulate the result. So the missing data that we need is from the work done from point 4 to point 1. Okay, so we will continue. So the shaded area here from point 4 to point 1, PdV. And we know that it is isentropic, so PV raised to the K is constant. We manipulate the integral here by replacing the value of P in terms of constant time and V. We know the value of K here. So yeah, V to the K, C, we can put the constant outside the integral sign. So we have this. So it is easy now to integrate. We have P4V4 raised to the K. And then we have V minus K dV. So this one will be the result. And integrating it, and So substituting the values, therefore, after simplifying it, we have P1B1 minus P4B4 all over 1 minus K. So substituting the values here, the result will be 0.799 kilojoules, or we can also write kilopascals times cubic meters. And then we tabulate the result here. The net work of the cycle will be the sum of these, the work done in each process. So negative 1.609, negative 0.7988, positive 2.124, positive 0.799. The result will be here, 0.5152 kilojoules. Tabulate the result. So we can see the result here, 0.5152 kilojoules. The next step is to solve for the displacement volume, V sub D. This displacement volume is simply V sub 1 minus V sub 3, and we have 0.01 cubic meters minus 0.001 cubic meters. We'll have 0.009 cubic meters. That will be the displacement volume. And what is required is the mean effective pressure, which is simply the net work divided by the displacement volume. You have here net work divided by displacement volume. So we have 0.5152 divided by 0.009. And the result will be 57.24 kilopascals. So this is the answer that is required. So thank you for watching our video tutorials, and please visit our YouTube channel for more video tutorials at H. Machacon Mechanical Engineering channel on YouTube. Bye now.